chapter, as we have seen, introduced the relation between work done by forces and energy. And now we will see also what is the definition of power. So power is defined as the amount of work performed per unit time. It is du by dt, where u represents the work. And when we derive the work with respect to time, we get the power. Another definition of the power, if we start from the definition of work, the work is F dot product dr, where dr is the displacement and F is the force. Then, if we do du by dt, if we just divide here the du over dt, then we will do the same for the second side. We will obtain F dot dr by dt. dr by dt is the derivative of position with respect to time, which represents velocity vector. So we can say that the power is equal to F dot v. Now, the unit of power is watt, which is joule per second. Okay. Now, what about efficiency? You know that in any problem or in any case, the output will be in general smaller than the input because we have losses. Okay, so in order to compute the amount of losses we define for a certain machine, we define the efficiency. The efficiency represents the power input output over the power input. Now, in case you have that the energy provided and the useful energy by the machine are occurring at the same time interval, then we can replace the power by this formula. It's delta energy, so it's energy, output energy over delta T. And also for the power input, it's energy input over delta T. Now, in case delta T is the same for both, at the same time of supplying energy, we are using it, then delta T will be simplified. And the efficiency can be computed as energy output over energy input. Now, don't forget that when we say we have that the power is F dot V, it's a dot product. Then if F and V are not collinear, we should project F on V, okay? Or V on F, but in general, we do F on V. So this is theta. So we should do F cosine theta times V, okay? Let us do an application on power and efficiency. The motor arm of the host operates with an efficiency of 0.85. Determine the power that must be supplied to the motor to lift the 375 Newton crate C at the instant point P on the cable has an acceleration of 1.2 meter per second square and a velocity of 0.6 meters per second. So in this problem, they gave us a motor that is trying to draw a cable in order to lift a crate. So this is the purpose. Now they are giving us the properties at point P, which is at the motor level. We know that the velocity at this point is given to be 0.6. And we have that the acceleration is 1.2. Okay. Now the question is to determine the power that must be supplied to the motor. So to start with, here for the motor, what can we calculate? We can calculate the useful power. So P output is the useful power that will lift the crate. Okay. This power will be equal to, what is the force developed here? It is the tension in the cable. So if I call the tension in this cable T, then the power output will be T times Vp. Here they are collinear, Vp and T, so no need to do projection because already theta is 0, so it's T times Vp. Now Vp is known, but the tension is not. So we should try to get the tension in order to calculate the power output of my motor. Okay. Now, how to calculate the tension? Let us see in this problem what do we have. We have a system of pulleys and a motor. So we have a system here. Whenever I have a system of pulleys, I can try to relate motion of block C and the motor coordinate, because here, as you can see, the motor is drawing the cable. So we can consider that if we take a certain reference line, this length is constant, but what is varying is what is going inside. So if you want the coordinate SP here, it is taking into account the total length going inside the motor. Okay. And we have, on the other hand, we have a block that is moving and it's connected to the center of this pulley. So we can take as a coordinate a vertical coordinate SC towards the center of the pulley of this pulley. Now, by doing this, we can relate the coordinate of the motor to the coordinate of C. So we can simply write that we have SP, which is the length that is going inside the motor, plus 2SC equal to a constant. So if we write SP plus 2SC equals to a constant, and we derive this relation with respect to time, then we can get that Vp plus 2Vc is equal to 0. And since we know the value of Vp, which is 0.6, then we can deduce what is the velocity at C. So, and also we can relate accelerations. Okay. Now, what is interesting for us now is to relate acceleration. Why? Because as we said, we need the tension. And to get the tension, we can take the free body diagram of the block. Because for the block, we have the weight, W, and we have the tension here, T, I will call it T2. Can you tell me what is the relation between T2 and T? I will clear everything here. Look, I want to relate the tension in this cable here to the tension holding the block. What should I do then? If this is T2 and this is T1, how to relate them, or T? What should I do to relate these two tensions? Look, this cable, we have the tension is the same over the cable here. Okay? So if I take this pulley as my system, I will have from this side T2, and I will have here 2T, one from the first side, one from the other side. So this is T and this is T. And since my pulley is massless, so I can write that sum of forces on my pulley is equal to 0. So 2T minus T2 equals to 0. And therefore, I can say that T is equal to T2 over 2. Okay? So T is equal to T2 over 2. And now I need to get something about the acceleration of C, because now I can write the Newton law for C to get the value of T2 and then deduce the value of T. Okay? We have already written the relation between Vp and Vc. It's the same for the acceleration. So we can write that acceleration of P, plus 2 times acceleration of C is equal to 0. And since we know that acceleration of P is 1.2, then we can deduce that the acceleration of C will be minus 0.6. Okay, so first we get AC. AC is equal to minus 0.6 from this relation. And once we get AC, then we can take the free body diagram of block C. So let us do it here. This is my free body diagram. We have the weight of C, WC. We have the tension here, which is 2T. And we know the acceleration of C. So we can write sum of forces. I will consider the positive direction downward. Okay, so we have sum of forces on C equals to plus WC minus 2T. And look, AC is negative because AC is minus AP over 2. Okay, so it's equal to M times minus 0.6. Okay, minus 0.6. Now I can, by replacing, I can get the value of T. And once I have the value of T, I can say that the output power is T times V velocity at point P. But it's not enough because they want the total power. It determines the power that must be supplied. This is the input. Okay, so now in order to determine the input, having the efficiency, I have the efficiency of the motor, then we can write that P input is equal to P output over the efficiency. Okay. Any question on this? Okay. Now, we will introduce the last part in this chapter, which is the conservative forces and potential energy. And I think that you are familiar with this. So, what is the definition of a conservative force? A conservative force is a force that for which the work is not depending on the path followed by the particle. It's just depending on the initial and final state. Okay? So, for example, if I take, let's say, for the weight, for example, we have developed together that the weight is given by, the work of the weight is minus W delta Y. So it just depends on the initial and final value of Y. Okay? And therefore, if we do straight, if you go straight from one point to the other, or if you go up and then go down, the work will not change if the initial and final positions are the same. Okay? Now, this is called a conservative force. And whenever we have a conservative force, we can define what is called potential energy, okay, related to the force. And in case in a problem all forces applied are conservative, we can apply what is called conservation of mechanical energy. Okay, so let us see how to do it. So the main forces that are conservative, we have a lot, but we have two that are very common: the weight and the spring. Why the spring also? Because also we have seen together that the work of the spring is also given by just It's a function of initial and final state. The work of the spring on a particle is half k delta S1 square minus half k delta S2 square. Okay, so it's also depending just on the initial and final state. So it's a conservative force. Now let us see how we define the potential energy related to these conservative forces. So first, for the gravitational potential energy, it's defined as W times Y, okay? And why did I put plus or minus? Because it depends on the sense you take for Y. So if you consider Y positive upward, you will have that your potential is plus WY, while if you take Y positive downward, then your convention will be take minus WY. Because whenever I select a reference line, okay, if I am above the reference line, then I have a positive potential, and if I am below the reference line, then my potential will be negative. Okay, so pay attention for this. Depending on your Y, if Y is upward, your potential is plus WY, while if your Y axis is positive downward, then the potential is given by minus WY. Okay, now concerning the elastic potential energy, okay, we have that the elastic potential energy is given by half k delta S square, where delta S represents the stretching or compression of your spring. So here, for example, if we consider the unstretched position as the origin of the displacement, then S will represent the stretching or compression, and therefore the elastic potential is given by half k S square. So for the elastic potential, it's always positive, but the difference, when we find the work, depending if delta S1 is higher or delta S2, the work can be positive or negative. Now, how to use the potential energy? Let us see together. So we will consider a very simple example. We have a ball that is attached to a spring. Okay. The ball is attached to the spring. Then the forces acting on it are the weight and the spring force. So let us here try to apply first work and energy on this. If you want to find sum of work of forces, so sum of work of forces in this problem is the work of the weight and the work of the spring force. So first, concerning the weight, the work, as we have seen before, when we consider a coordinate downward, it's expressed as plus W delta S. So the work of the weight is plus W delta S. So it's plus W S2 minus S1. And concerning the work of the spring on the ball, it is plus half k S1 square minus half k S2 square. Okay? Now, if we try to compare with the potential energy, we have defined for a coordinate, for an S coordinate downward, V gravitational is given by, as we have seen now, it's minus W times S. Okay, so if you look at your expression, you have WS2 minus WS1. You can replace WS2 by minus V gravitational 2. And you have minus WS1 is plus V gravitational 1. Now, concerning the potential energy, elastic energy, you have here minus half Ks square So it's minus V potential at state 2. And you have plus half KS1 square, which is plus V potential elastic at state V elastic at state 1. So what can we deduce from this? We can deduce that the work can be replaced by the total potential at state 1, which includes gravitational here and elastic, minus the total potential at state 2. Okay? So we can express the work in case we have conservative forces. Another way to express the work is to say that the work of forces can be replaced by the variation in potential energy. And if we replace now in the principle of work and energy, you know that sum of work between state 1 and 2 is equal to the difference in kinetic energy. So it's T2 minus T1. Now, if I replace sum of work by V1 minus V2, then I can deduce that if I take T1 to this side and if I take V2 to the other side, I have that T1 plus V1 is equal to T2 plus V2. So this is called the conservation of mechanical energy or conservation of energy. And it states that during the motion, the sum of the particle kinetic energy and potential energy will remain constant. Okay? Because we don't have any source of losses. Because when a force is conservative, this means that I will not have losses. Okay? Since the work is independent of the path, it will be the same when I go from one position to the other. So if I go from one position and I go back to this position, then my energy will remain the same. So this means that my energy is conserved. Okay. And of course, in case I have a system of particles, then I can write that summation of kinetic energies at state 1 plus summation of potential energies at state 1 will be equal to summation of kinetic energy at state 2 plus summation of potential energy at state 2. Let us see an application on this. Let us consider the following structure that is used to test the response of an airplane during a clash. The plane of mass 8 megagram is hoisted back until theta equals to 60 degrees, and then pullback cable AC is released when the plane is at rest. Determine the speed of the plane just before clashing into the ground, where theta is equal to 15 degrees. Also, what is the maximum tension developed in the supporting cable during the motion? So we have an illustration of the problem here. We have a cable. The cable is attached to an airplane. Now, what we will do is the initial angle between the two is, between the vertical and the cable is 60 degrees. And now what we will do is that we will cut this cable. So the airplane will do, if you want, an oscillation. And it will, in case you don't have here the ground, it will oscillate. But since you have the ground, it will have you will have a shock between, a collision between the two. The question is to determine the speed of your airplane just before hitting the ground. Okay, so first they want us and the question was first to determine the speed just before the clashing with the ground, and second to find the maximum tension developed in the cable. So let us start first by the velocity. So we need to determine what is the velocity just before the clash. You have here that when collision will take place, This angle is 15 degrees, they told us. So in this problem, how we can think? First, we know the initial